Tuesday I left you with a couple of questions about a perpetual motion machine. So I said you have a perpetual motion machine of the first kind which violates the first law. It creates energy out of nothing. And these are often quite subtle to try to figure out what's going wrong. But it's one of the second, perpetual motion machine of the second kind violates the second law. Why would this be such a wonderful thing, even though you're not creating energy? Very simply, suppose you could, violate the second law would be to pump heat uphill to higher, from low temperature to high temperature without putting in any work into it. This doesn't violate the first law if the total energy is conserved. So suppose that, in this room at 22 degrees or whatever, there's a lot of heat in this room. It's not at absolute zero. So I could use, if I had this machine that would pump things uphill without having to put in any energy, I could take the heat from some of the heat in this room and use it to boil water. Okay. Now the room would cool down a little bit from 22 to 21.9 degrees as its heat was used to heat up the water. So the heat is transferred from the room at 22 degrees to the water. I boil the water. I use the boiling water to run a turbine, and I get my work. Now I haven't violated the first law because no energy has been created. I've used the energy in the room, the heat in the room, but I've converted it 100% to work. And that can't be done. You cannot, in a heat engine, convert 100% of your heat to work. You can convert some of it, but you're always going to have losses, and you can't pump heat uphill. Everything, then we could just keep going around forever, and we could just be, the heat in the room would form the work, we turn the turbine, eventually the turbine all goes to heat in the room, and the room's everything's back down to 22 degrees, and everything's fine, but we keep getting work for nothing. So, perpetual motion machines of the second kind violate the second law, generally by pumping heat uphill. There's other ways of doing it too, by separating. You could imagine if you had here I have a little turbine. Here's my turbine. Spinning around. Here I have a gas, and here I have a vacuum. Okay, so I open this up, and the gas goes over to the vacuum and turns the turbine, and I get energy out of it. Now what I do is, until the gas is half on this side and half on this side. Now what I do is I take all the gas on this side, put it back on that side. Okay, creating the vacuum again here. It takes no energy because it's an ideal gas. Get all the gas back here, and I run things again. Okay. I'm violating the second law. I'm making the system more ordered. So that's a perpetual motion machine of the second kind as well. Okay. We can't do it. Okay, so that brings us to Maxwell's demon. Maxwell's demon did create a perpetual motion machine of the second kind. Maxwell's demon sat here, and here was the thing, and there was a gas over here. Let's do it. Yesterday I did it in terms, or Tuesday I did it in terms of him separating gas. Let's do it this way. Here's the gas, here's the vacuum. Okay, here I have my little turbine, and the gas runs as a turbine. Now what I want to do is now I have gas on both sides. So now what I want to do is I want to get all this gas back over here, so I've got a vacuum here again, then I can run the turbine again. So what I do is I have a little trap door, and here I have my little demon, horns, and the demon, whenever he sees a gas molecule coming this way, he opens the door and lets it through. With one coming this way, he closes it, and after a while he's managed to get all the gas over on this side without putting any energy into the system. Okay, and now we run the whole thing again. Okay, and I said, what's wrong with Maxwell's demon? He's violating the second law. He's not violating the first law, but he's violating the second law because he's making the universe more ordered. He's taking the gas that was here and letting the molecules one at a time go over here. Okay, separating them, and then from that I can convert all things back into work. Okay, so what's wrong with Maxwell's demon? Why does this? It appears that he's decreasing the entropy of the system. The whole thing is insulated. He's decreasing the entropy of the system in seeming violation of the second law. And I said they went through theological arguments that this, yes, he can do it, and this shows his intelligence. Because he's an intelligent being can violate the second law, and this is an argument in favor of free will, the soul, God, whatever. Okay. Actually, then, and it was not till the 1948 or so that people come up with the idea, but it's kind of simple. Suppose you replace the demon with a computer. That should work as well. Somehow you have a thing, the computer can detect the molecule coming one way and open the door. Okay? you've got to remember there's an entropy created inside the computer. The computer, if the computer was the same before and after the process, the computer couldn't be doing anything. The computer is not independent. You got to, yes, the entropy of the gas is decreasing, but the entropy of the computer is increasing. You can think there's a register in the computer. It has to say, yes, there's a molecule coming. So in this register, I say 1, there's a molecule coming, and now I open the gate, and now afterwards, the computer's entropy has increased. Now you have to reset the computer back to 0 for the next molecule coming through. The entropy of the computer is increasing. It is not, if the computer had no change, if there was no change in the computer, then it couldn't be doing anything. It's doing something, and there's entropy being created in the computer. If you have, at the absolute minimum, you put 1 gas molecule goes from this side to this side, now you know where it is, you've decreased the entropy by 1 bit, and you have increased the entropy of the computer by at least 1 bit, because you've had to put a 1 in a register somewhere to tell it that the molecule is coming, open the door. Okay, so that would be an absolutely reversible situation in which the total entropy was 0, but in reality, of course, it's not going to be ideal. So the entropy of the daemon or the computer is going to go up faster than the entropy of the gas and the total entropy. The problem was looking at the daemon as being independent from the universe. He's part of the universe and he's part of the whole affair. And when you think of a computer, then it becomes rather obvious. The computer is a machine, obviously something's happening in the machine. And it actually goes back to the theological argument that the whole problem with why didn't people realize that now in the daemon, if it's an actual little man, then it's not a computer, but his brain. In the daemon's brain, the entropy is going up. Okay, the problem is that we tend to think of ourselves, our thinking as not being a physical process. Our thoughts are not part of the universe. Our brain isn't a physical thing. Our thoughts are some ephemeral thing. So the daemon was managing to do this without any physical change going on in his brain, but we know that isn't the case. And that shows the other way around. It was a theological argument that got us on the wrong track. It was thinking of our thoughts as being independent of the universe. It was wrong. Once we realized that our brain is part of the universe and entropy is going on in our brain, we realized that we cannot violate the second law. And it's interesting that it took people that long to realize. Nobody had the argument, well, what's going on in the brain of the daemon? Even some of the best scientists never sort of put that up. And then Shannon in 1948 said, well, yeah, but the daemon's brain is a physical thing. Okay, that's the daemon. That's Maxwell's daemon. Still, some people don't believe it.
The question is the problem.
Yep.
For the membrane that make osmosis, there is the same kind of phenomenon that let pass some molecule but don't pass on the other side.
Yeah. How does that work? You build up the pressure on one side?
No, for example, I have in mind some liquid that let pass salt but don't come back.
Yeah, well, that's just a physical phenomenon for some reason, mechanical or chemical reason, that can't go the other direction. But you can't separate things that way because you'll eventually build up a pressure on one side, which will...
Yeah, okay.
Well, why won't it permit it to? Okay, okay, I see your question.
Probably it was when you spoke last time about this. I was thinking about this problem and I was not finding why it's possible to kind of let pass in one direction some salt and don't let it on the other way. But probably.
Okay, what do you think about it? Give me a moment to think about that one. I don't want to waste everybody's time. You're creating, it can't be, you're creating entropy. How does it? I see your question. If we have a, why would it not go?
Maybe there is a kind of saturation that at one point you have to remove your membrane.
Yeah, I think that's similar to a question that makes the daemon even more interesting. Is let's take the whole daemon out of it. And here I'm going to put a small door, zero mass. Okay, and the door has a small spring which closes the door. But it's a very weak spring because the door has zero mass. So if a molecule, so the door is closed. If the door is closed, normally the door is closed like this. Molecule coming this way, the door stays closed. It bounces back. Okay, but now what you have is if the molecule, as the door goes this way with the spring here, if the molecule comes this way, it hits the door opens. The molecule goes through, if the spring brings the door back shut again. That way the gases get separated and there's no demon. Okay, let's think about that one. Plus your osmosis question for next week. The two together. The two are related. Why doesn't this work? And we say, well, you can't make a door, but let's assume that these are really super heavy molecules and the door is very, very light and the door will close again. Why, what's the problem? Okay. You see the thing, it's a very light door. It goes this way, it opens the door, it comes back, can't go that way. I think that's basically your osmosis question. A one-way trap door. And you don't have anything happening in a computer. What am I doing here? Why am I thinking? What was I doing? Why did I get? Oh yeah, okay, that's what I was looking for. So, we have one other type of, this is figure 10. Okay, this is another kind of, this is figure 10 from the chapter. This again is another type of, I guess you could call it a predominance diagram. This is now a two-component system, copper-oxygen. And what I plotted here is the horizontal axis is the temperature, the vertical axis is RT log PO2. Okay. Or in other words, this is the, where PO2 is the equilibrium partial pressure of oxygen. Okay, so you have a given temperature, you have a given equilibrium partial pressure of oxygen. So again, same idea, you have a box, you fix a PO2, you put some copper in the box, you fix a temperature, you let the thing reach equilibrium. What do you have at equilibrium? Okay, so at this particular temperature, say 400 degrees, if your oxygen pressure is very low, you'll have copper. As you increase the oxygen pressure, you'll reach a point where the reaction's at equilibrium. Copper plus oxygen gives you Cu2O. Okay, so if you're having copper, 2 copper plus oxygen equals Cu2O, half oxygen Cu2O, then there will be an equilibrium constant, which is 1 over PO2. 1/2, and when the pressure is such to satisfy that equilibrium constant, you'll have Cu2O. If you increase the oxygen pressure more, you'll reach a point where the two oxides are in equilibrium. If you go higher, you're in a one-phase region, and so on. Okay, as you take copper solid, as you increase the temperature at a certain point, the solid melts to form liquid. This is the melting point, and so on. If you were to take constant pressure and Cu2O, say a constant pressure of oxygen over Cu2O, and you were to increase the temperature, at a certain point the Cu2O would dissociate. Okay, so now you're taking this reaction, the equilibrium constant is changing as you change the temperature. So as you heat it up and heat it up, the reaction tends to go more and more to the left, and eventually it dissociation. Okay, so once again, you have one-phase regions. If you have if you had this temperature and this PO2, you'd have only copper. So if you're anywhere in these one-phase regions, there's only one phase at equilibrium. Only on the lines would you have two phases, and only at the triple points would you have three phases. And once again, you see that it's the same geometry of this diagram: one-phase regions, two-phase lines, three-phase points. Okay, but now I've managed to. In the previous diagram, the predominance diagram, PSO2, PO2, that was at constant temperature. Okay, now it's at now I'm allowing the temperature to vary as well. Do you know what an Ellingham diagram is? Everybody? Okay, well, if you have the formation of an oxide, you have, M plus whatever oxygen equals MO2. Delta G 0 is equal to minus RT log 1 over PO2, or equal to plus RT log PO2. So basically, the x-axis here is delta G standard for the reaction. Okay, so I've plotted this here as a phase diagram, an equilibrium diagram. I'm saying this line here, what I've said, this line here is an equilibrium. Let's look at it as a phase diagram. At this temperature and this oxygen pressure, this is the stable phase. At this temperature and this oxygen pressure, this is the stable phase. This is the line where the two phases are in equilibrium. In a Ellingham diagram, what you do is you plot the Gibbs energy of formation, delta G0, versus temperature. So you don't look at this as a phase diagram, you look at this as simply a plot of the Gibbs energy change as a function of temperature. But the Gibbs energy change is RT log PO2. So this is just an Ellingham diagram, can be looked at as a curve. This is a curve of delta G standard for this reaction. For this reaction I have a delta G0. And I can say I'm plotting, this is the way an Ellingham diagram is presented. I'm plotting delta G0 as a function of temperature. This is just a line on a graph of delta G0, or the other way of looking at it is this is a phase diagram and this is a phase boundary. Here you have a one-phase region, and you have a two-phase boundary. So it may serve to elucidate it, it may simply serve to confuse you, I don't know. But an Ellingham diagram presented in this direction is a phase diagram. Those are not. This is a line of plotting delta G0, or it's a phase boundary. Yeah.
For Ellingham diagram, is it always on the right side the metallic phase and on the left side the oxide?
In an Ellingham diagram, it's always forming the oxide, yeah, and it's always for 1 mole of oxygen. This is so you can compare things. So if you plot an Ellingham diagram, you'd have delta G0 versus temperature. So if here you had, say, you'd have 2 PB plus oxygen equals 2 PBO. Gives energy for that reaction. And the delta G0 then is RT log 1 over, minus RT log 1 over PO2, or RT log PO2. If you were to plot, say, titanium, it would be Ti plus O2 equals TiO2. Always 1 mole of oxygen. So this is always RT log PO2. And why is it 1 mole of oxygen? So you could compare them. Titanium is more reactive than lead. This would simply mean if you wanted to do the reaction between them. So you would have, will titanium reduce lead oxide, or will lead reduce titanium oxide? Okay, you want to then, you write 2 PbO plus titanium equals TiO2 plus 2 lead. That's the balanced reaction. This here is, the oxygens cancel out. This reaction is this minus this. So the oxygens cancel. So now I just look at the Ellingham diagram and I see that the titanium line is below the lead line, so the delta G for this reaction is negative, because this line is below this line. Okay, it's just when I subtract the two Gibbs energies, the oxygen cancels out. If I were to plot everything, if I were to plot a per mole of metal, then it wouldn't necessarily be the case. It just, plotting it this way, it gives you, the Ellingham diagram gives you the order. The metals that are at the bottom are the most reactive, the oxides are the most stable. That's it. So this is an Ellingham diagram, if you like. This is the Ellingham diagram for, this is the Ellingham diagram here, this way. This is the Ellingham diagram for copper plus oxygen gives you Cu2O. This is the Electrochemical diagram for Cu2O plus oxygen gives you CuO, the higher oxide. On Electrochemical diagrams, you often have a little M like this to indicate the melting point on this line. Electrochemical diagrams, you don't draw this line. On an Electrochemical diagram, you would just have this line, you'd see a kink here, and you'd see another kink here, and you'd see an M here, and here you see a little M in a box to tell you that that's the melting point of the metal, and that's the melting point of the oxide. Okay, so the Electrochemical diagram for copper and Cu2O would be this line, but you wouldn't have this little vertical line. If I draw in the vertical lines, now I've got a phase diagram. All right, let's talk a little bit about measuring thermodynamic properties. Okay, the Gibbs energy change, as we've seen, the Gibbs energy change when a system is at equilibrium, G is equal to 0. We have delta G0 is minus RT log K. If I can measure the equilibrium constant, I can measure delta G0 for the reaction. The equilibrium constant is the ratio of the partial pressures in the simple case at equilibrium. So I set up the system at equilibrium and I measure the property of equilibrium. So consider the reaction for reaction 35. What was reaction 35? Carbon plus oxygen equals CO2. Okay, so I take carbon plus oxygen equals CO2. I take a furnace here, I put a little boat in the furnace containing carbon. I pass oxygen very slowly. That's not what I want, did I want? Was reaction 35. Might as well try to beat some soft ships way back here. Alright, that's what I wanted, okay. Two CO plus carbon equals CO2, that's better. 2 CO. CO2 plus carbon. I want to measure the Gibbs energy change of that reaction. Okay? The delta G0 for that reaction is minus RT log PCO2 over PCO squared at equilibrium. Okay, so if I can measure the ratio of CO squared over PCO2 over PCO squared at equilibrium, I measure the Gibbs energy change of the reaction. So I put in my furnace at a temperature T, I put some carbon. Here I pass a mixture of CO and CO2, which is approximately equal to the ratio I expect at equilibrium. The gas equilibrates. It goes slowly, you pass it slowly at temperature here, then equilibrium is established. Either carbon reacts with the CO2 or some CO2 deposits carbon. And then at the exit, I assume that I have PCO and PCO2 are approximately their equilibrium values. Okay, so I measure PCO2 and PCO at the output, either by spectroscopy or some other method. And then I have the two partial pressures, I put them into here and I get delta G0. Okay, so the general way is you measure the Gibbs energy change of her, and that gives me the Gibbs energy change, not at equilibrium, but the standard Gibbs energy change. So I measure the Gibbs energy changes generally are measured by establishing an equilibrium. So you can actually get delta G of a reaction without actually carrying out the reaction. You let the thing reach equilibrium and you observe the equilibrium conditions. That's generally how you get delta G. This is a simple example, but in all cases where you're measuring delta G somehow, you're setting up an equilibrium, measuring the equilibrium conditions, and then working backwards to get delta G. Another common technique of establishing equilibrium is by means of an electrochemical cell. A galvanic cell is designed so that the cell reaction can occur only with the passage of an electric current through an external circuit. Okay, so that's what an electrochemical cell is. You have an electrochemical cell, you have a cell set up so that the only way that the chemical reaction can occur is if you pass a current through an external circuit. It cannot occur by direct chemical reaction.
what would be a good example?
Oh, it's the formation cell. This is a graphite rod dipping into a bath of zinc chloride. Over here you have a rod of zinc. And here I have Okay, so here I have a bath of zinc chloride, liquid zinc, solid liquid zinc chloride, let's say, which is an ionic material, conducts electricity ionically. Here I have a zinc electrode made out of zinc metal dipping into the zinc chloride. Over here I have, let's say, this is a glass apparatus, let's say a glass tube with a carbon rod, just an inert electrical conductor, and I'm passing chlorine gas over here. So here, this whole container here is bathed in chlorine. Now, zinc plus chlorine forms zinc chloride, but the zinc and the chlorine can't get to each other because they're not in contact, so nothing happens. Okay. But let us suppose that here I put an external electrical circuit. So I put an external electrical circuit, and now what can happen is the following. At this electrode interface here, between the electrode and the zinc chloride, you can have zinc. The zinc chloride contains zinc ions, and it contains chlorine ions. Okay, it's a molten salt containing zinc ions and chlorine ions. At this electrode here, the zinc metal produces 2 electrons plus a zinc ion. Okay, the zinc goes into the solution as an ion, as zinc ion, giving up 2 electrons. The 2 electrons move through the external circuit over to this electrode over here, and at this electrode here, the 2 electrons react with the chlorine gas coming through to form 2 chlorine ions. And the total, then, if you take this reaction and you take this electrode reaction and you add them up, you end up with this reaction. So as you close the external circuit here, if I open the external circuit, if it's open circuit, nothing happens. If I close the external circuit, allowing the electrons to move, okay, then what happens is the electrons move around here. This reaction occurs at this electrode. This electrode reaction occurs at this electrode. You add them up, the electrons cancel, and zinc and chlorine are reacting to form zinc chloride. If you run the cell, you'll find you're forming zinc chloride. This is called the formation cell. Now, there's obviously now a driving force for these electrons to do this. And let's suppose that I keep an open circuit. I have an open circuit, but here I put a voltmeter. Okay? Now, there will be no current flowing, nothing will occur, but I'm going to measure a voltage, which is not 0. The voltage is going to be related to the driving force of this reaction. The stronger the driving force for this reaction, the bigger the voltage is going to be up here. And in fact, the voltage is directly related to the Gibbs energy. Now, in this case, if I'm running, suppose I run this reaction, I close the external circuit, I just put a short circuit here. I'm going to get a fast electric current. Now the system's not at equilibrium, it's running. How do I make the thing at equilibrium? Well, it's kind of a matter of, it's like the gas in the piston. How do I let the piston move very slowly? I put my hand on the piston and I apply an external force equal to the internal force and allow it to move very slowly. I do the same thing here, if you like. I put an external voltage here. I take an external voltage which wants the current to go the other way, and I apply this external voltage until I find the current is 0. I put an ammeter here. I measure the current. If I don't apply, if the external voltage counteracts the internal voltage that's trying to go. If my external voltage is too low, I measure a current going this way. If it's too high, the current's going to go that way. I change the external voltage until I observe a current of 0, and then I know that or it's like the same in here. If with pressure in the piston, if I wanted to measure the pressure of the piston, I could put my hand here, I could put a thing, and I could, when I find an external pressure equal to the internal pressure, such as when nothing moves, then I know I'm at equilibrium and the external pressure So I measure, I look at the external pressure that I'm applying, and it's equal to the internal pressure. Now anyway, when the current's running very, very slowly, this is basically what a voltmeter does. That's a reversible process. Okay, so the reversible voltage, which is the voltage at zero current, is going to be related to the driving force of the reaction, which is the Gibbs energy change. Okay, so if you want to do an external voltage is applied which is equal in magnitude but opposite in sign to the cell potential, so that no current flows. And then the system is at equilibrium, so it's a reversible process now. So that dz coulombs pass through the external circuit. E is this voltage that you measure. When you apply the external voltage equal to the internal voltage, we use E because it's electrochemical potential, I apply an external voltage E, volts, and I adjust E until I see that there is no current flowing, and then I say E is now the cell voltage for this overall cell reaction. So now I permit dz coulombs, say, to flow through the external circuit at equilibrium. So I allow dz coulombs to flow very, very slowly, so the system's at equilibrium. So now I'm doing reversible work. So E dz joules of work are performed. E is joules per coulomb, volts is joules per coulomb, so E dz is the number of joules of work performed. Since the process is at equilibrium, this is a reversible non-pressure volume work. dW, reversible non-pressure volume. Taking old equation 19, which was dG is VdP minus SdT plus sigma mu IdNA plus dW reversible non-PV. You can go back and look at where that came from, but that's just from putting all the various things together. That's another form of the, well, go back and look at this. This comes from the fundamental equation of thermodynamics. And now we have a closed system at constant T and P. It's a closed system, so all this term is zero, dNi is zero, pressure is constant, temperature is constant. Okay, so dG at Tp and N is equal to the non-reversible PV work. Okay, if I'm running this cell as a closed system at constant T and constant P, the non-pressure volume, this is non-PV work. This is certainly work. It's doing work. It's not a heat term, it's an EdZ. So you're doing electrical work. You could use that to run an electrical motor or something. Okay, so it's W non-reversible. Okay, so the cell reaction is formulated. We formulate this. This is the overall cell reaction. And the cell reaction is formulated such that the advancement of the reaction by dxi moles is associated with the passage of dz coulombs. Okay, so delta G dxi is the energy change, and that's equal to minus E dz. So delta G is minus Fe. Okay, so I measure the energy change. I measure the voltage here at open circuit. F is called Faraday's constant. Delta G is the Gibbs energy change of the cell reaction, which is this is the reversible non-PV work from this equation, and this is the reversible non-PV work, where F is Faraday's constant. It's simply the number of coulombs in a mole of electrons. So actually I formulate the cell reaction so that when 1 mole of cell reaction occurs, actually I would have to formulate it this way. I would have to put 1/2 Z, 1/2 Z plus 1/2 chlorine equals 1/2 ZnCl2. And now I'm getting 1 electron per mole reacting. Okay. Because this form, I said when we run the reaction here, you're getting 2 electrons, so doing it this way you get 1 reactant. Okay, so when 1 mole of zinc chloride is formed, 1 mole of electrons have passed through the, okay. F is Faraday's constant, it's the number of coulombs in a mole of electrons. Faraday's constant is a constant, a universal constant. So we have Faraday's, you have this is called the Nernst equation. This thing here is called the Nernst equation. And the Nernst equation relates the Gibbs energy change of the cell reaction to the open circuit reversible voltage of the cell. Okay, because you're doing, it comes from this equation up here then, the Gibbs energy. The general, dG at Tp and N is equal to dW reversible non-PV. So I arrange the reaction, I design my cell so that the cell's running a constant Tp in a closed system, and I try to remeasure the reversible non-PV work as the reaction proceeds. And this is one way of doing it. You set up an equilibrium cell, you measure the equilibrium voltage. That's the general principle of an electrochemical cell. Now you can design all sorts of electrochemical cells. You design an electrochemical cell, you take a reaction for which you want to measure the Gibbs energy change, whatever it may be, and then you try to design an apparatus such that that reaction can occur only by the passage of an external electrons through an external circuit, and then you measure the equilibrium voltage. If you can design the cell so that whatever reaction is occurring is the one you want, then you end up measuring the Gibbs energy change for that reaction. You have to be very certain that can only occur. The problem is, of course, that supposing now, and this is the case, in the molten salt, you might find some chlorine gas dissolves in the molten salt as chlorine gas moves across and reacts directly with the zinc. In that case, of course, things aren't going to work. If the zinc and the chlorine get in contact, then no current flows, they just react chemically. They have to react only by the passage of a current. So you also have to design the cell so that this is the only way for it to occur. You must not permit any direct contact between the electrodes. Okay, so that's the principle of an electrochemical cell, and in any electrochemical cell, that's what you're trying to do. You're trying to design the cell so that you get an equilibrium reaction only by the passage of electrical current. Then whatever the cell reaction is, the Nernst equation applies. Okay, so that's how, anyway, that's measuring Gibbs energy. Once again though, just like the previous example where you have measuring the PCO and PCO2, you're setting up an equilibrium and you're measuring the equilibrium conditions. You're setting up the system at equilibrium. At equilibrium, no current is flowing, and you're measuring the equilibrium conditions. You measure the equilibrium conditions, you get the Gibbs energy change. Measuring enthalpy change. I said the enthalpy change can be measured directly by calorimetry. We talked about a bomb calorimeter. You actually run the reaction from reactants to products, and you measure the heat in the calorimeter. That was a bomb calorimeter. If you want to measure a heat of mixing of two liquids, a heat of mixing in your optimizations, you take A and B in a calorimeter, you mix them, and you measure the heat that comes off. You want to measure the enthalpy change for a reaction, you carry out the reaction in the calorimeter and you measure the heat. There's another way of doing it. Alternately, if delta G is measured by an equilibrium technique, as we just talked about above, then delta H can be determined from the temperature dependence of delta G. Okay, from equation 48 for a process in a closed system. So here we have, taking this expression here, we're having a closed system. Let's assume that this term is 0. It's not an electrochemical cell. So these two terms drop out. We're also going to keep the pressure constant. So a system in which there's only pressure volume work, closed system, constant pressure, we end up with dG dt is equal to minus S. Okay, so at constant pressure in a closed system, the rate of change of Gibbs energy is equal, with temperature, is equal to minus S. You can also rearrange this equation a little bit, and you end up with an equivalent expression that dG over T, d1 over T at constant P is equal to H. Now these equations apply to both the initial and final states of a process. Those two equations, let's say the first equation, number 52, applies to a specific compound. But let us say I have a system A plus B produces C as my chemical reaction. Okay, so for this reaction, delta G is G of C minus G of A minus G of B. Okay, delta S is equal to S of C minus S of A minus S of B. Okay, but dG dt is minus S, so d delta G dt, so d delta G dt, putting this expression here, d delta G dt would be minus SC minus SB minus SA, or in other words, minus delta S. Okay, so this applies to B. Okay, so if you can write dG dt as minus S for a pure material, you can do the same thing for any chemical reaction. d delta G dt is minus delta S. So if you've set up a system to measure delta G, then you measure that as a function of temperature, and the difference is, and the slope is minus delta S. Okay. Or just rearranging it, it's the same thing. You can show that this is just take the expression G is H minus, delta G is delta H minus T delta S, substitute that in here and you'll end up with this. It's the same thing if you plot delta G T versus D1 over T. So this is simply, say I measure, I have the reaction, CO plus carbon, 2CO plus carbon plus CO2, for example. I measure delta G. Delta G is minus RT log K. As I said, I've set up the equilibrium. I measured the equilibrium constant. I've calculated delta G. I measured delta G naught, as we just said, by setting up the equilibrium. So now I've measured delta G naught is equal to minus RT log PCO2 over PCO squared. So as I said, I set up this thing in a system. I let it reach equilibrium. I measure the partial pressures of the output. I get delta G at that temperature. So for this reaction, I get delta G naught at a certain temperature. Then I repeat I set up the equilibrium at another temperature and I get delta G naught at another temperature. So I have several experiments where I measure delta G naught as a function of temperature. And then I draw a line through here and the slope of the line is minus delta S of the reaction. Okay, so you can measure delta S of a reaction by measuring the slope. Or let's do it differently. Let's plot delta G naught over T versus 1 over T. Just another way of plotting the same results. And now I got a line here. And if I draw that line, the slope will be equal to delta H. Okay, so I measure by setting up an equilibrium, and this could be measured by the gas equilibrium, or the delta G measured from the electrochemical cell. My cell I just showed you, zinc plus chlorine forms zinc chloride. I could set up the electrochemical cell and measure the voltage, giving me at a given temperature, gives me the delta G. I do that at several temperatures, draw the line, I can get the entropy of the reaction. Okay, or the heat of the reaction if I do it that way. This doesn't have to be a straight line, of course. This can be a curved line. In that case, delta S will vary with temperature. Suppose it is a straight line. Suppose it is a straight line. Okay, then we know that delta G is delta H minus T delta S. Now, if it's a straight line, that means delta H and delta S are constant, independent of temperature. In which case, obviously, the slope is minus delta S. And if I were to extrapolate this back down to 0 Kelvin, that would be the heat of the reaction. In actual fact, of course, it's curved slightly. But even though it's curved, the slope at any temperature is equal to delta S at that temperature. And the same thing here, I could write delta G is delta H over T minus delta S. Sorry, delta G over T is delta H over T minus delta S. So clearly if I plot delta G over T versus 1 over T, the slope is delta H. And now the intercept down here at 1 over T is 0 is going to be delta S if it's a straight line. So this is interesting because this means now I can measure delta H of a reaction without actually doing the reaction. In a calorimeter, you actually have to carry out the reaction from beginning to end and measure the heat. Here the reaction is not carried out, it's only systems equilibrated at different temperatures, and it gives you the heat for the reaction. This applies not just to reactions, it would apply to anything. If this was the Gibbs energy of mixing, then the slope of the Gibbs energy of mixing versus T is the entropy minus the entropy of mixing. If this is the Gibbs energy of fusion versus temperature, the slope is minus the entropy of fusion, and so on. Okay, but you can measure, this is another way of measuring the enthalpy. You can measure the enthalpy as the temperature dependence of the Gibbs energy without ever carrying out the reaction. Clearly, experimentally, this has some problems because this is derived quantity. You're not measuring directly S or H, it's the slope of another, it's the difference between two measurements, which is always less accurate than measuring something directly. You're not directly measuring H, you're measuring the change in G, so it depends on, you have to measure, it's the difference between two measurements. If the temperature range, now it all depends on the temperature range. If your temperature range is very small, then obviously a very slight error can cause a big error in delta H. If you've got a big long temperature range, then things a lot better. Generally, this is not measuring, so this is a way of measuring entropy. Now this doesn't measure S absolute, this measures delta S. It measures delta H. It measures the change in entropy for the process, doesn't measure the absolute entropy. Okay, this method of measuring entropy, by measuring the Gibbs energy change, by setting the system up at equilibrium and taking the slope, that is called the second law method of measuring entropy. For obscure reasons. So if you read in a paper measurements of entropy were made by the second law method, this is what it means. The second law entropy was measured in this fashion. You'll often see in your work that somebody's measured the electrochemical cell, by the way. You can use electrochemical cells for measuring activity, for example. If you can set up your if your cell reaction, we'll do this later, if your cell reaction is for the material going into solution, you're measuring the RT log activity, you're measuring the partial Gibbs energy electrochemically. If this is the partial Gibbs energy, RT log activity of a component, then the slope is the partial entropy. And the slope of this line is the partial enthalpy. Okay, so generally the electrochemical cells are good for measuring the partial Gibbs energy, the activities, RT log activity, but the second law method is not so good for measuring S and H because in general the temperature range is quite short and errors in slope can be quite high. So just realize when somebody says the H and S were obtained from electrochemical cell measurements or whatever that you're not talking about. The question then is how accurately was the slope measured? The delta G can be measured very, very accurately, but I mean, you've got to be careful. The delta G can be very, very accurate, but if the temperature range is small, even though this is very accurate, the delta H and delta S can be very inaccurate. Very slight difference here and slight difference here can change the slope tremendously if the temperature difference is very small. So there's a danger in that. There's another way, another method of measuring enthalpy. Entropy involves the third law, which states that the entropy of a perfect crystal of a pure substance at eternal equilibrium at 0 Kelvin is 0. This follows from the definition of entropy as K log, from the Boltzmann definition of entropy, K log multiplicity. In the classical thermodynamics, it has truly a law. The second law of thermodynamics says that delta S is Q reversible over T. As I said, they've observed there's an absolute zero. For the same for all substances, but it's a law. Okay, there's no way you can derive it from the other laws. However, if you define entropy as K log T, then obviously when T is 1, the system's perfectly ordered and the entropy is 0. So the entropy of a perfect crystal of a pure sum, blah, blah, blah. Okay, so let us first, so for a perfectly ordered system at absolute 0, the entropy is 0. Let us first derive an expression for changing entropy as a function, as a substance is heated. Okay, combining equation 52, dH dt is Cp. You can find that dH dt is Tds dt. Okay, look back at equations 52 and 53 and convince yourself of that fact. And so the entropy change is between two, the entropy change for heating something, heating a substance from T1 to T2, the entropy change is the integral of Cp over T dt. Remember the enthalpy change, Ht2 minus Ht1 is the integral of Cp dt. The entropy change is the integral of Cp over T dt. Okay, so the entropy change, if you measure the heat capacity of a substance as a function of temperature, you can calculate the entropy change for heating. You measure the heat capacity in the calorimeter, as we talked about. So the entropy, so you measure the heat capacity in a calorimeter, either a drop calorimeter or an adiabatic calorimeter, as I discussed last week. And that'll give you the entropy difference. But now, since if you put T1 as 0 Kelvin, now you know that ST1 is 0. So now, if you can measure Cp down to 0 Kelvin, you can obtain, from the heat capacity measurement alone, you can obtain the absolute entropy of the system. And that's called the third law method of obtaining entropy. And this is why you will see in material science, metallurgical literature, and so on, the heat capacity measured in the area of 2 to 3 to 10 Kelvin. You would wonder why would anybody care about what they practically care about what the heat capacity was down there. This is why, if you can measure it accurately down there and extrapolate the last few degrees to 0 Kelvin, you can obtain the absolute entropy for the thing. And this is very useful. Alright, so you just got to measure the heat capacity down to absolute 0, or very close to absolute 0, and there's all sorts of literature on how to extrapolate it the last little bit where you can't measure it. Of course, you got to be sure that you're going down to a perfect crystal at 0 Kelvin. You don't have no residual disorder if you cool the thing quickly and everything, you'll end up with residual vacancies, maybe residual grain boundaries, and so on. You've got to have a perfect crystal, and the thing has no residual order in it. And you got to get close enough to absolute zero, and then there's ways of extrapolating based upon the physics of vibrators and so on, but we won't go into that. But this is a pretty well-established technique, and that's why people worry about measuring heat capacity at low temperature. So now supposing I have the reaction A plus B plus equals C, and I would like to know what the entropy change is for that reaction. The entropy change is 298. Now one way of doing it is the second law method. I set this thing up as some sort of an equilibrium and take the temperature dependence. Or del S naught of 298 is the entropy of C minus the entropy of A minus the entropy of B at 298. I obtain each of these individual entropies by the third law method. That is, I measure the heat capacity of C from 0 Kelvin up to 298, and the same thing for the heat capacities of A and B. And then using this equation here, I obtain the absolute entropies of the three materials, and then I can calculate delta S 298. And this is rather interesting because it means that I've obtained the entropy of this reaction without ever having the reaction. I'm sort of making the reaction, or English word here, or metal block, without ever having the reaction occur, without ever putting A, B, and C together, okay, without ever affecting the reaction. I can measure the entropy. What I do is I have three separate experiments, one on each pure material, and from that I obtain delta S of the reaction without ever having the reaction take place. And unlike the second law, well, okay, it's sort of similar with the second law method. The reaction isn't taking place, but at least you have to establish equilibrium. Here you don't even have to establish an equilibrium. The reaction never occurs, nor do we even establish an equilibrium. A, B, and C never have to come together. Okay, I just measure individual experiments on the three materials, and that gives me the delta S of the reaction. So that's the third law method. It also means the third law means that the entropy change for any reaction among any three materials at 0 Kelvin is 0. Hence, it is not a convention. Okay, I've seen this in the thermodynamic textbooks. I can show them to you. They say we have the convention that the enthalpy of a pure element at 298 Kelvin is 0. That is a convention. Okay, and then it will say, and the convention for entropy is that the entropy of a pure compound, blah, blah, at 0 Kelvin is 0. That's not a convention. That's a law. Okay? Any three substances I put together, they don't have to be elements, it can be anything. But any three substances together at 0 Kelvin, the delta S is 0. That's not a convention. That's the third law of thermodynamics. Because you can't do this with enthalpy. I can't measure the heat capacity of a material between 0 Kelvin and T to obtain the absolute enthalpy, put them together and get delta H. You can't do it. You can't measure. If you want to measure the enthalpy, you either have to carry out the reaction, or you have to establish an equilibrium and measure it as a function of temperature, but you got to put the stuff together somehow. Okay, with the entropy you don't have to. Difference. So that's what I just said here. And the auxiliary functions, I just did this too. I showed that dg is Tp is less than 0 is a special form of the second law for a process at constant T and P. And here's another way of what I showed you, that the change in entropy, the change in internal energy. The change of internal energy, well, I did this one here. A is U minus Ts. So I said that the change in Helmholtz energy is equal to minus T delta S total at constant T and V. So the general form of the second law is that the total entropy change is positive. This is a special form of the second law for a process at T and approaching equilibrium at T and V. This is a special form of the dg at T and V is negative is a special form. If you want to play around with thermodynamics, you can also show that if you carry out a reaction at constant volume and entropy, then du must be negative, because this is, well, if the system's at constant entropy, there's no entropy change in the system, so du is minus TdS total. But how the hell do you carry out a reaction at constant entropy? That's kind of a question. dH at constant pressure and entropy. So these are special forms of the second law as well, but they require somehow that you visualize how you're going to carry out something at constant entropy, which can do, but this is not practically terribly useful stuff. Okay, but you'll always see that. Okay, so a couple of hours. Okay, I guess we could maybe wrap it up at this point. You have any questions on things I've said so far? Yeah, we'll get into that. For reading material, you might look at this number 3, ideal solutions. Just that's the quick derivation of the ideal solution laws and so on. You might want to look this part over. Not up to here, just the first part, just up to here. First, whatever, 3 pages of the number 3, ideal solutions. I'll read that over. And I'll be talking on Tuesday about partial properties and chemical potential and so on. So this was number 4 of defining what partial properties mean, what activity means, chemical potential. Now we're getting into solutions now finally. So you might want to look at that, which is number 4, partial properties, and the ideal solutions, the first 2 or 3 pages. Okay, because next week now we're finished. I finished pretty much with the pure materials and fundamental thermodynamics. Now I wanted to get into solution thermodynamics. Look those over also for reading material in this chapter. Please read for sure sections 2.7, chemical potential. 2.7, chemical potential. And then go to section 4. Which starts on page 33, section 4, and read section 4, all of section 4.1 plus the subsections. Okay, all of section 4.1 and all 4.1 and all the subsections, as well as section 2.7 on the chemical potential. And you might want to look over, as I said here, the first 2 or 3 definition of ideal solution, the derivation of ideal solution from Boltzmann equation, and I'll be talking about exactly the definition of partial properties, what we mean by partial, Gibbs energies and chemical activities and so on. And to practice a little bit with what I've talked about so far, you could do the following problems from the homework problems. That would be section 4, which is about entropy concepts, 1, 3, 5, and 6. Section 5 is on equilibrium constant. These are really straightforward equilibrium constant type calculations. As I said, you don't have to do all of these. Look at them. If you say, oh, that's trivial, I know how to do that, well then, as long as you're certain, don't bother. The order here that I'm putting them in is what I consider to be kind of a logical order, going from simpler to more reverse, or that's the order that I would look at them in for section 5. They say these are fairly straightforward chemical equilibrium things that you really should understand. Look at them, try them if you don't understand them. I will put up the, on the website, I will put the answers up on Monday morning. And then on Tuesday, I'll discuss those that you asked me to discuss, only those that you asked me to discuss. Okay. And then next week we'll try to do the whole basic idea of chemical potentials, properties of solutions. And then we're ready to start talking about solution models. And then we'll have completed my fundamental thermodynamics thing. Unless maybe we should do phase diagrams, no? After all, that's what this whole thing's about. I'll think about whether we should talk about phase diagrams at that point or not. Maybe that's what we should. Okay. All right, 1, 2, 3, ha.